Hello everyone, and welcome to today's webinar, Advances in EBSD for Geological Materials, the Impact of Spherical Indexing and Experimental Master and Pattern Simulation. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We'll attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we'll follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Sean Wallace joined EDAX in 2015 as an applications engineer specializing in EBSD. He has a strong background in all sorts of instrumentations, including EBSD, electron microprobe, all sorts of mass spectrometry, and computed tomography. In his career, he's taught researchers of all levels, from postdocs to undergrads, how to use instrumentation, and he continues that here at EDAX in Gatan. Sean earned his Master of Science in Geology from the University of South Carolina. His research focused on method development for ICP mass spectrometry and geothermal barometry to help better understand planetary differentiation. After earning his degree, Sean worked as a scientific assistant at the American Museum of Natural History in New York City, where he helped study the origin of the solar system using EBSD and other instruments, including 3D work with computed tomography. Sean hopes to bring these 3D skills to the rapidly expanding 3D EBSD world. When Sean is not busy running samples, he can often be found in nature, either hiking or fishing, or just staring at rocks. Now over to Sean.
Hey everybody, it's nice to be here. And again, this is kind of a little bit of a niche kind of presentation, so I'm happy to see the numbers that we do have here. So yeah, I really want to kind of talk today about the what we really have for the new tools we have to kind of show you where we're going and how these new tools impact specifically how we do geological EBSD. Again, do be forthcoming with the questions. I can do a pretty good job of answering the questions as they come up. So again, I'll try my best to keep up with questions as they do come in, which is a little bit different than normal. So let's go ahead and kind of dive into to this here. And again, I do have to apologize to my moderator there. Throwing the word geothermal barometry in there is pretty mean for somebody who's never seen the word. So again, I do apologize for that, but that is a long, tricky word if you've definitely never seen it before. So again, my goal here is really to kind of show you some of these new tools we have with getting orientation information out of our data. And with that becomes a little bit of background knowledge, with specifically how we currently kind of do it as the default method. And the default method is what we call the Hough transform. So the Hough transform is pretty straightforward. It's used for a lot of things in computer-wise, and it's essentially the Hough transform turns your pattern over here on the left-hand side. This is what the Hough transform is, and the purpose of the Hough transform is basically to, make these like little light dark spots, which are correlated to lines, and then these lines are then fed into basically an algorithm to find the orientations. So again, these little points here become lines. These lines then become intersecting angles, and these angles are then compared to what's called a lookup table. And then from there, we can basically do a little voting algorithm and get the orientation information off of there. And again, this works incredibly well and has been robust for a very, very long time, and is kind of the default method and has been the default method for 20 plus years, 30 years now of EBSD, and it's because it works. And it works very, very well. And it's kind of been the standard because of that. So it's nice. The reason we use it live is for a couple different reasons. It's very fast, and it's robust in many situations. And of course, we can increase that robustness when we use NPAR. And again, NPAR is our patented algorithm, basically doing spatial pattern averaging. Now, there are some minor cons of the Hough transform. The Hough transform is really you really have to make sure, especially for geological materials, this is really kind of focusing on geological over here on the right-hand side. So with this, the best reflectors can be a challenge for some materials, because with geological materials, we're going to see that, sometimes it's these weird, kind of these off reflectors that can really give us the information that we need to make sure we're getting correct orientations. It struggles with poor quality patterns. So again, because I need often that little fine detail here, if the Hough transform can't have enough information to find what I'm looking for, we're going to run into some issues. The angular resolution can be a little bit, it's fine at this level for most things, but the angular resolution is around, let's say, half a degree or less. And that's useful for most things, but sometimes we want it to be a little bit better. And then finally, of course, there is some difficulty recalling what we call pseudosymmetry. So again, these very small differences in things can sometimes be large in orientation space, and we need to be able to do that. And then finally, there's going to be this what we call non-centrosymmetric materials, which again, these fine details are going to be key for. And honestly, what I often find for the geological side is you really have to know your structure very well to fit your material. Because again, these lookup tables that the Hough uses is basically usually calling for an ideal structure. And the geological side, we're often, I always tell people we deal with nature. Nature is, is a fickle creature. And because of that, we often have to worry about solid solution materials, natural deformation, and just in general, again, we're not metals, right? Again, so we're not dealing with usually more, lower symmetry, easier materials. We're dealing with things that tend to be a little bit more tricky. And if you ever learned EBSD on the geological side, it's a little bit more tricky. Now, the Hough transform is basically what's called an inverse problem. And this is where I get kind of a little bit out of my lane because I'm a geologist, not like a computer scientist. But an inverse problem is basically where you're comparing your data to a system. So in this case, we're comparing our Hough data to that lookup table to basically get the information we need for the orientation solutions. Now, the inverse problems is basically, it's mathematically ill-posed. And what we mean by that is it's pretty computationally complex. And because of that, again, it's computationally, it takes a lot of power. Now, what we can do with this, we can do what's called a forward problem, which is basically what we call pattern simulation. And a lot of people know this as dictionary indexing. And of course, kind of the follow-up to that is what we call spherical indexing. And that's where you really compare your system to the data instead of the other way around. So this gives a couple different advantages here, is because, and we'll talk about those advantages in a little bit of detail here. So in this case here, again, it's basically how are you comparing the information you have versus your system. In this case here, we're basically modeling the system to put it on our data with these new approaches. Now, one thing I'll remember, this is one of the things I always kind of forget, so I'm going to kind of mention it here, is things like NPAR and spherical indexing are currently done post-processing, which does require saving patterns. So nowadays, it really kind of push users and people in general to make sure that you're saving patterns to do this kind of work after the fact. Again, you can often get great data on that first kind of run-throughs here. But again, if you do save the patterns, it allows you to use these tools that are available to you to really kind of dive a little bit deeper into your data. Now, that first real kind of forward modeling approach that came out was called dictionary indexing. And dictionary indexing, I don't want to spend too much time on it, but I want to kind of give you an idea of what it does and how Spherical is different than it. So what you would do for dictionary indexing is you take the pattern you collected off the scope, you then would create a dictionary and then compare it to all the guys in the dictionary. And in the end, you get the best match off of that. Now, when you do this approach, there's some downsides to this dictionary approach. And this is kind of getting what the main thing here is you have to build the dictionary is kind of one of the issues. So over here we have our crystal information, our lattice parameters, where everything is, your SEM conditions, you have your beam geometry, then run through a model, and then you basically sample your model in orientation space. Then you actually would build the dictionary in the end, and you have this huge dictionary of all these different patterns. So again, kind of go over that. You start off with basically your system information. You run it through your modeling software, and then you basically get your dictionary off of this based off of how you sample your orientation space. And of course, these master patterns, are created by dynamical diffraction simulations, and basically doing the entire energy range. So you go and look at basically the entire energy range. You would do little kind of a discrete steps, and in the end, you would you basically combine all these together to get your master patterns. And this, depending on your materials, can be relatively quick. Some FCC materials take like 5 or 6 minutes on most computers, and then some of the lower symmetry materials, this can be quite long. And again, that's one of the kind of the downsides of the older dictionary methods. You'd have to redo these master patterns depending on their conditions. So again, when you're actually building this, you want to make sure that you're getting uniformly information across the entirety of orientation space. So you'd actually have to build these libraries targeting the specific kind of step size here. So again, dictionaries are discrete in their construction. So if I'm looking to kind of make something, I would do it like, every, let's say, half a degree. I would have to make sure I did it every half a degree in the full orientation space. And those could be quite large, especially for lower symmetry materials. Again, there's big fancy words up there like cubicorric, which really kind of talks about this. And then here's the next slide that I'm going to show people, and most people have no idea what this is because I honestly don't fully understand Rodriguez space either. But this just kind of gives you an idea of the kind of the spacing required to fully get this 5-degree spacing through the entirety of orientation space. So again, each one of these little dots here is basically again a pattern that I would need to be able to again have a dictionary for the entirety of orientation space. Now, and here's kind of again a little bit of a more of a, I think, an easier way to see this is that each one of these little blocks here is basically again a pattern that I need to save for the entirety of orientation space. And again, this here you can see is you have your different directions here. And again, these dictionaries can be very large. It's also kind of a brute force approach. Again, when you're doing these dictionaries, you have to have the entire dictionary, and you have to compare your pattern to basically everything in the dictionary. And this is where the geological slides start to become a problem. So with the geological side, we're usually dealing with things that tend to be a little bit lower symmetry, which is going to be over here on the left. Over here on the right-hand side, we can see to look at cubic space to get relatively high angular resolution. I'm in the, let's say 15, 20 million patterns. As I go to more lower symmetry materials, we can see this really starts to ramp up quite fast, and where the triclinic spacing can be, you can kind of start to see here how many patterns you're looking at here. Did I have my thing wrong? Yeah, this is like 5 million. I think I might have misspoke a little bit there earlier. But again, you can see that the dictionary size for some of these lower symmetry materials becomes quite large. So if we're doing geological indexing with multi-phase samples, just the dictionary alone for, let's say, 3 phases could be just a crazy amount of information that we have to have stored and available to us. But there are some pros, again, to the dictionary method, and the main thing is it's more robust than the Hough. While it is definitely slower, but again, it is much more robust, specifically with low quality patterns, again, lower symmetry materials, deformed materials. The dictionary indexing has its place in things. I think the craziest data set I've seen really for dictionary indexing, again, I know a lot of geologists here are here, but there's a process called shot peening, which is basically shooting metal balls to toughen the surface of materials. And those are completely beat up materials. And dictionary indexing does an incredible job in that material. And that's really kind of the first data set I saw that really said, oh, wow, this is really robust, because the patterns there were just destroyed. There's very little information in the patterns because of how deformed this material was. That said, it is significantly slower than Hough indexing. Again, Hough indexing live, we go fast, so that's why we usually want it. And again, the angular resolution and dictionary size can be a problem. There's also a relatively steep learning curve for dictionary indexing, because you have to learn how to make the master patterns, understand dictionary spacing, and then how we kind of do this general refinement stuff, which I'm not even going to touch about today. But again, just realize that dictionary indexing did have these learning curve that we'd have to go through. Now, let's say instead of like kind of a dictionary method, let's say I could do something a little bit different, and kind of do something a little bit more robust. And what we can do with that is we can start doing these cross correlation techniques of image processing, and kind of go from here. This kind of holds true for dictionary as well, but this is kind of the first step here. And you can see here, basically, this would be like your pattern, and then it would basically run it through the algorithm to figure out where it best matched this hotspot would be what we did. So this is again kind of how it works in general. And this works for basically any sort of image correlations. But what if I could do it on a sphere? Well, again, because of the way EBSD works, if I have this master pattern, I can then basically do a cross correlation of my pattern from my experiment and figure out what this is. This is basically what spherical indexing is doing. We're taking our master pattern, we're doing our detector, and we're doing a little bit of fancy math on the end because we have to kind of, do some weird things because, again, this circle here is a projection onto the master pattern based on the geometry. So this pattern right here actually comes from down here. So again, we have to do a couple, we'll call them distortions, but we have to do a little bit of a good question. What's the best word for this? Someone called it distortion, a transformation from our patterns to be able to correlate it, more closely to the actual master pattern. So again, we have to do this to be aware. Again, this is kind of how we do it. But again, this is, what we're doing behind the scenes when we're doing this spherical indexing. Now, if there are any math nerds out there and who really kind of fully understand this stuff, there's a good paper out here by Will Lenthy and Mark DeGraff and this gentleman here that was published not too long ago, back in 2019. We call this spherical harmonic transform approach. And this is where the spherical indexing comes from, is this math. And this is just a fancy mathematical kind of term here to kind of do this. So again, you're basically just taking your little projection of your phosphorus screen here and then putting it kind of going backwards to get what you need to. Now, mathematically, this is much faster. So this is why we do this, is because it's more robust and it's faster when we're doing things post-processing wise. So this whole spherical indexing approach is, for the most part, replaced dictionary indexing. It's as robust as dictionary indexing. It's faster. It provides more orientation refinement, and more importantly, especially for the geological side, there's no pre-calculation of the dictionaries. So again, if I was doing geological samples with 3, 4, 5 samples, these could be huge. Now, of course, it is more robust than the Hough, but it was also much slower. Well, I mean, it can be slower. Nowadays, it's actually pretty fast. I pulled this slide from elsewhere. I'm not sure I really believe all this more. It can be slower, but not always. But it's much more robust with like weak patterns, heavily deformed materials, or rough surfaces, fine-grained. These phase differentiation and pseudosymmetry problems, as well as non-pseudosymmetric materials. So yeah, we really kind of have again to be able to deal with some of these geological problems we have, and just kind of show you how well this kind of works here. And this is again stuff I find truly mind-boggling. Just kind of in the 10 years I've been with EDAX here, is this pattern here, or this pattern right here that I'm looking at, has enough information to get perfect, basically perfect EBSD data out of. So again, we always want to get the best patterns we can, but oftentimes, we're controlled by what our sample is. So we can get these low quality patterns where we can turn into perfect data sets. And again, that's just mind-boggling to me. Even something like this, where you can't really squint and see anything on it, where the Hough again has not enough information, we're getting usable-ish data sets out of here. So again, we can see that again, this forward modeling approach allows us to get much more data out of systems and materials that we might have a little bit, hard issues coming out of. And just kind of an example here that I love showing here, because I think it's time for a pretty map, is one of these samples that, we got okay data sets back with. And this data set here on the right, I believe at this point is like 10 years old. So this is a brachiopod. So a brachiopod is a little sea critter. So it had these little holes in this, and it's just basically how it builds its shell, and it kind of like built these from these little, I think they're called siphungles, but don't hold me to that. And here you can see this initial data set that we collected, again, literally a decade ago. Again, kind of shows the crystal structure, but nothing too crazy. Now, if we run it through these modern approaches with the same data set that we initially collected a decade ago, we can turn that data set into this data set, which to me is just mind-boggling. So again, you can see the better definition. We can see this much finer grained material, and you can see the finer, just finer detail in general. So again, these new kind of things like NPAR and spherical indexing allowed us to really kind of do things. In this case, the main issue with this sample was that we had these relatively low beam currents because it's biological material. So biological materials can't take much beam current without getting damaged. So there's little information, but here, again, because of these newer techniques, we're able to do this. So in general, though, the problems of geological samples really kind of mirror the issues with the Hough. So, determining the best reflectors for this can be a challenge. This is one of those things I don't think most of our users really kind of fiddle with all that much, but when you're dealing with different materials and lower symmetry materials, those reflectors, what I'm actually building the lookup table off of, can be very, very kind of tricky to figure out which one is more important. And that's, again, I think something that, again, most users don't even really dive into. It struggles with poor quality patterns. So the Hough has issues with these lower quality patterns. And the thing that caused those would be things like conductivity, low Z, or deformation. So those are three problems that we often have with geological samples. Well, most of them are conductive. Oftentimes, we're looking at them because they are deformed, and we just tend to be low Z in general because we're silicates and other things like that. And of course, the angular resolution is going to be, depending on what we're looking at, with the given pattern quality usually. And I'm going to show you guys some examples of pseudosymmetry / non-pseudosymmetry kind of things we're doing this. And of course, your structure must be known and fit your material. And again, if we have solid solution deformations, our structure often doesn't quite fit our material because it's a little bit different. Now, one of the things I've kind of glossed over here, and I think is important to understand here, is that, again, the Hough basically reduces the entire pattern to a series of points, which are kind of lines. Spherical indexing in the dictionary approach is using every bit of information in the pattern. So we're not taking any, we're not basically losing any information here. So intensity changes, very minor changes in the band positions, all that kind of stuff is taken into account. So even small things in the end really kind of matter. Now, of course, the problem with the dictionary indexing I've kind of approached here already is that constructing and storing the dictionary for multiphase samples is honestly not fun. The time involved in master pattern information can sometimes be, can take a while. Again, do I need to rebuild a master pattern for every small change in solid solutions? Feldspar kind of things. Forced rate versus phthalate. Again, what do I need to do to make sure that I'm getting the right master pattern for a material? And of course, how well does my sample match the phase file that I'm using? Again, can I use a forced rate 95 on something that's 50-50? Well, maybe. But again, this is something you have to test, and to test that, you have to basically build a dictionary every single time. Now, one of the things we've actually kind of come up with here is something that I'm probably, it's one of the things that I really want you guys to think about, and more importantly, if you have data sets, this would be something that I can get myself in trouble with, but this is where the things I want to see how useful this can be for you guys. So what we've done is take some work by Dr. Day and kind of incorporated it in some ways into our software, basically saying, hey, I have patterns. Can I reconstruct the master pattern without even doing the dynamical simulations? And if I do that, I'm basically making a master pattern that matches all my experimental conditions. So my geometry is all set, my intensity, all this kind of things is basically, in the end, I'm going to be comparing my experiment to my experiment. And because of that, I'm getting around some of these kind of deviations that may exist in the dynamical simulation and what I'm doing. This is what we call, again, experimental Kikuchi sphere reconstruction. So if I have enough high quality patterns in my material, and I know the base structure of my material, I can essentially reconstruct this by finding the orientations of the patterns that I have, and then build my master pattern from doing this. And this is the crazy part here. This is right here is for nickel. You can see the dynamical simulation takes 8 minutes, while the experimental takes around 3 seconds. Well, what about the geological side? On the geological side, here's my good old forsterite, here's my astatite. I go from 16 hours to 15 seconds. Now, this also, I think, gets into some details that I think are kind of important about the dynamical simulations. Again, one of my favorite sayings is models. Models are always wrong. The question is are they useful? And here we can see the dynamical simulation versus the actual information that we have in the patterns. There are quite some differences. And these differences, again, are caused by the actual system itself that we're not really accounting for, like phosphorus green blooming, or again, minor changes in your materials. And again, you can see that things like this little zone axis here, look and behave much differently from your actual experimental data. So again, these look pretty close together, but if I can actually use this experimental information, better matches what I'm actually collecting, which makes me, basically starting from a better point. And here you can kind of see these patterns that we're using to basically build these off of. So over here, I have an olivine pattern, and of course, I have a whole data set with this, again, that we turned into this master pattern. And here's the type down here that we turned into this guy over here. So again, instead of having to rebuild this dictionary or dynamical simulation every time, I can just use the experimental side and go from like 16 hours of reconstruction to less than a minute. And these experimental master patterns work, very, very well. So here's kind of an example here of the Hough having trouble with some orientations in olivine, where these, running these spherical doing is pretty fast. So again, here you can see again, it goes relatively fast on this computer. This is controlled by your GPU, by the way. So it's one of those things we always talk about how fast it goes, but the more computing power you throw in, of course, it's going to be faster. So here you can see this is their experimental pattern. Here's actually the dynamical simulation, and here you can see the dynamical simulation is actually having problems in some areas. But because the experimental actually matches it better, it's not having the kind of the issues here. So again, in this olivine sample here, we're getting really good indexing over the whole area. Again, where the Hough was having some problems, like here, again, the Hough was just completely just not doing its thing. And here you can see that we're getting nice consistent data over the entire area when we use spherical indexing. So again, by combining things like spherical indexing with the experimental master patterns, we're getting better information off of these geological samples. And again, we chose olivine kind of here on purpose because it's one of the most common minerals, if not the most common minerals on Earth. And again, this is kind of showing you on a more of a multi-phase sample using olivine that here using the magnesium as kind of as a proxy. You can kind of see that it does a really good job of phase discrimination as well. So the actual, here's the kind of the phases down here. We can see these big bright spots. So what we're looking at. So the experimental master patterns, it does a good job at doing the actual just pulling it apart without having to deal with things like chi-scan. Now we actually start looking at kind of the data here. I want to show you kind of the quality of the patterns that we're getting and still getting highly coherent data. So this is the sample. I'm going to show you the actual sample data a little bit later on here. But this is just kind of a pattern that we got off of a garnet. We ran it through NPAR. So a little bit of slide here on NPAR. This is one of those things where you're kind of in the EDAC sphere, you know what NPAR is. So we use by default a hex-based sampling grid, and I can tell you why. It's a couple different reasons, but our main thing is it allows us here, because we use it, we can look at our neighbors. So this is what we call neighbors, neighbor pattern averaging and reindexing. So NPAR lets me look at my nearest neighbors. So if I have a hex grid, I have 6 nearest neighbors. And then of those nearest neighbors, I can basically add all those patterns together to increase the signal noise ratio. So instead of a pattern like this, I now have a pattern like this. And then if I compare this and get an orientation off of this, so this is, we run through this through spherical indexing, get an orientation off of it. And this right here is basically the orientation solution that we get. And this, the orientation here is from the dynamical simulation. This, I think, is where you really start to understand what the advantages are of spherical indexing with geological materials. So if you start looking at things like garnet, like down here in this pattern over here, we can see there's a good zone axis right here. We can see that in all 3 of these. So as collected here, I can see, a couple of pretty straight zone axes, which is probably enough information, believe it or not, to get probably a decent Hough orientation. But if I start to need finer details to get good orientation information off of geological material, finer level details that I'm looking at here. And this is what we start to see. So you see, like, there's a little band here and a band kind of like right here parallel to it. Well, that is these guys. So this very fine level of detail really helps me start to get the information here. And this also how I kind of ground truth it when I'm doing this kind of work, is if I can see this kind of fine detail here in my pattern, and I can tell that my simulation has got the same thing, it's giving me a pretty good idea that, I'm making sure that I believe what the software is telling me. Another one on this guy pattern right here is like this guy right here. So you can see this pattern right here, or this line right here, that parallels this guy. It's right there. So again, if we can start to kind of see these crazy ones, and there's another one like right here and right here. So garnet is pretty straightforward. This is honestly the one I'm a little bit more impressed by. Here's a hornblende. Again, I personally haven't had, hornblende's tricky. So again, here's the pattern as measured. Again, in super low symmetry material, very busy Kikuchi patterns in general. We can see that there's hints of lines basically all over the place. We run it through NPAR. I can start to see, some of the information a little bit better. And of course, I compare it to the orientation solution that we get, and we can see that we do a pretty good job here. So you start looking through here, you can kind of see that, like this line right here, just, we're just nailing it. This line right here. And then, there's some of these cross-cutting ones, like this cross-cutting one right here. I can see it in the NPAR, and it's like, I could probably see it a little bit here if you squint. So again, the Hough transform, finding something like this, finding 8, 9, 10 lines to get a good orientation for a geological material, we're gonna have some problems probably. So again, having the ability to turn, not the best patterns in the world into data that goes on. Now, let me just kind of step back a little bit. Again, I always tell people you should try to start better with the best patterns that you have. Now, a lot of times the issue is, we only have limited microscope time. So because we collect the data once and be able to reprocess it, you don't always have to go back to your microscope, tweak a little bit of the setting to get better data. We can kind of just do what we have here. So again, I always tell people that these tools I'm showing you are there to help you, but we always want to start with the best possible. And for geological samples, often the prep is going to be kind of the hardest part because we have multiple samples, and I have to kind of pick and choose. Okay, hey, this prep does best for this phase. This phase is kind of with it. Well, this kind of lets me like not have to worry about that as much because I can kind of, okay, hey, I'm getting good enough in this phase. The harder phase, maybe I'm nailing really good with sample prep, and we're good from there. Here's scapulite, again, another kind of crazy kind of symmetry material here, where again, you can see that NPAR does a really kind of good job of nailing what we're looking at. And again, it's kind of the same thing here. I'm not going to focus too much more time on this, but you can see that these like lower symmetry lines we're really kind of starting to nail here that we couldn't really kind of see before. Again, this pattern up here is probably a little bit more impressive than this one because, again, we're really like nailing some of these kind of low symmetry lines. Here are good old fed plagioclase. Again, everybody's favorite mineral over here. Again, we can start to see the same kind of ideas here with these minerals. It can be very tricky. That we're doing a really kind of a good job here. So again, there's like no real information that we can see up here. Now we're really kind of nailing the zone axes, and again, a lot of these cross-cutting lines that I can't see in the patterns as collected. And of course, CPX, because hey, why not? It's why not do it. And this was just in the sample that we had for this data here. So here again, we can see that again, not the best quality patterns, but we're nailing this orientation. Again, you can see this axis. We can see these cross-cutting lines. We can, again, like this is crazy to me that we can see these two Kikuchi lines here and going on, but I'm probably dragging on a little bit. And of course, quartz as well. Again, look how busy this area is. Look again how good we're nailing all these kind of the secondary lines. And here's titanite as well. In the end, this is what we get from this sample. So this sample was all this data that I previously showed you is from this sample here. So this is a single field scan of this myelinite. Here we can see the all these different phases in here, and we can see large scale coherent kind of information from this. So this phase map here is again showing me these relatively large garnets. Then over here we can see the more of the scapulite with what's the other color down here, a hornblende over here, and of course the different minerals as we go through here. So again, here we can see large and small grain materials, very coherent, and again it's a really kind of a high quality data set. Down here is my scale, which might be a little bit hard to see, but this is roughly 1 millimeter across. So we're doing a relatively large map here with a relatively fine step size. Of course, here we can say, hey, we're geologists. We often work on much larger samples. So now you can see my scale bar down here has gone to 3 millimeters. So here we can see this is what we, this is basically an image quality map, what we call nowadays a SCI map for spherical indexing. It's a little bit different how it's calculated. But here again, you can see this grain structure. We see these big, large grains. deformation inside the grains. And of course, we can see again all this fine grained material around here. Again, look at the scale of this thing. So this is basically a full thin section all the way across and up. There we go. So again, with using both NPAR and spherical indexing, we're able to get these relatively high quality, large maps over these incredibly large areas. And again, this is something that is becoming very routine to get these. Again, I mean, we're nailing every single little tiny grain in here. We're doing a really good job on, including these deformation band structures. So yeah, this is kind of where we're going in the geological world, is we're able to do this kind of stuff really, really good. I mean, we could do it pretty good before, but now we're really kind of nailing the stuff in here. And here's the orientation map. So again, I can see that I'm getting really high quality data on this deformation structures. And again, if you really zoomed in on here, which I can't really kind of do live, but here's a little inclusion in this guy down here. Again, you can see very fine level deformation across a lot of this material. Again, some grain fracturing up here. And of course, this area down here as well. So again, this is where we're looking at the very large area mapping all into one shot. There are details on one of these maps about how big this was. I think it was 25 million data points. So this is roughly 25 million data points that was collected in an overnight run. Now, again, this is talking about mapping in large areas, but let's start talking about some specific kind of more crystallographic problems. So this right here is our good old friend marble, where I have calcite and dolomite, and we can see that the structures here are pretty close together. So I look what's called the A to C ratio of these two minerals. They're pretty close, but of course dolomite does have a little bit of difference here because we are throwing some magnesium in with the calcium. Now, if you're one of the lucky few 10 or 15 people who saw me at GSA in 2023, I actually had a kind of a more of a structured talk on this, where I talk about, can I see ordered and disordered phenomena in calcite? And if you're interested in that, let me know. But here we can see this relatively ordered magnesium, where I have it in this here. If we look down from the top, you can see the magnesium structure here. So this right here is the two differences between the calcite and dolomite. And you start looking at these, you're going to have a lot of problems finding major differences. But luckily enough for us, the computer does see them. But here again, you can see the calcite. Here you can see the dolomite. And the nice thing about this is I can actually kind of flash them back and forth. So over here on the left-hand side, you can see there's that 3% difference here between the calcite and the dolomite. You can kind of see these very small differences here. Now, depending on your orientation you had, this can be a very difficult problem for the Hough-based transform, because again, certain orientations, the amount of differences here is going to be pretty small when we do this. And again, this is going to be what we call a pseudosymmetry problem. Over here on the right-hand side is actually dolomite versus dolomite. So again, certain orientations of dolomite, in this case, we're rotated 180 degrees around the 110. You can see that again, there's not that much differences between these two patterns. So again, the Hough is going to have problems with something like this dolomite, kind of pseudosymmetry problem over here, because there's not much differences in that. We actually look at a data set here. We can tell the dolomite from the calcite pretty straightforwardly by looking at the magnesium map. And of course, if I do phase analysis on this using EDS data with chi-scan, we can see we do a pretty good job of pulling this apart. If I start looking at the orientation information, I can start to see that I'm having a little bit of difficulty with some materials here. So I can see I'm getting some speckling in some areas because of the pseudosymmetry problem that I don't really, I can't tell the difference in Hough-based indexing. What happens when we use spherical? Well, here you can see that spherical, does a really good job of pulling this apart. I'm not going to talk about, again, the bandwidth kind of thing, but to realize that, again, if you ever set up the Hough, the Hough-based indexing has, I think it's 13 parameters. Spherical indexing has one. And it's just because bandwidth. And it's basically just how it's measuring in frequency space. So the higher bandwidth you do, the longer it takes, but it's able to see finer level details. But again, it's one of those crazy things I find about the spherical indexing is that it really bends the learning curve for EBSD because the parameter space is so much smaller. Now, of course, with this, again, having a better pattern center fit is good, but we've built an algorithm for that, which kind of helps us get a little bit more differentiation on some things. But in the end, when we do kind of do all of our tricks that we have available to us over here, I can start to see some pretty major differences in that data set that we just collected. So here I've just pulled out just the dolomite information, and this is going to be a royal we because this is connected by my colleague Renee Declos over in Europe, which I believe is most of the data is actually collected by Renee. So big shout out to Renee for honestly doing most of the heavy lifting on this presentation. So now here, there's a big grain down here that was speckled in the previous map. We can see is now basically this domain structure of these two orientations. And if you look down here, this is basically the differences here is how we're looking at it here. So now if you look, you see the very minor differences between these two patterns. So this right here is the blue orientation. This right here is this reddish pink orientation. You can see that most of the lines are shared between these two. So for the Hough to get consistent indexing, it needs to find the lines that these two do not share. Here again, you can kind of see these kind of blinking back and forth between these two patterns. Is that this line here is kind of the big one that I really need to be able to find to really kind of tell these two kind of apart. If not, it's going to be some of these other kind of secondary lines that again we're seeing in the Hough. So again, we really kind of need to see this fine level detail where again the Hough is basically reducing this to a series of points. So, and then I'm just not going to see this in the Hough. Here's kind of doing this for this whole data set here. Again, you can kind of see the same idea here. Again, let's grain right here, kind of follow it back over here. You can see that all these zone axes are basically in the same place, but the differences between these two orientations is really found by again a couple of these tertiary lines here. And again, this is this power here of this is even this fine level of detail that we have now in these patterns. Comparing them to the master patterns really allows us to find these small details that we would just be ignoring in previous kind of EBSD maps. So in the end, we really have this large range of tools here available to us that really kind of change how I'm doing geological EBSD. So I don't really need to worry about making sure my reflector list is perfect anymore because there's no need because I'm using full pattern information. So I don't have to tweak the Hough to make sure that the things going into the Hough are the lookup tables and all those kind of things are perfect because I'm using all the information I have. I don't have to worry too much about poor patterns. Again, I always want to start with the best that I have, but I'm robust against noise. So again, if I do have some noise, as long as there is information in there, we can do a pretty good job of pulling the information out. So again, if I see material deformed or again, sample prep was tricky. We're really bending the learning curve here to allow EBSD to be, on the geological side, to be more easily used by everybody. Pseudosymmetry and non-symmetric materials. Yeah, again, we can see that, it turns it into in this case here for the marble, a pretty trivial problem. I'm not really having anything that's going on. And then, from there, we're doing a pretty good job with, what we're doing. And then finally, the structure of your material must be known to fit material. Well, experimental reconstruction of this really kind of fixes this and circumvents that because we're using, our experimental data to kind of match that. And this is where I think it's going to be really interesting for some of these feldspar problems that we often run into with very minor changes in solid solutions that can really kind of change things. Well, here I can kind of just, work around that problem to say, okay, this is this. Go ahead and make this phase file based off of what I'm telling it is. So again, we do that from there. Now, so with that in mind, I really kind of open it up to you guys to ask some questions. So feel free to ask me what information you have and not from there and go from there. Now, one thing again, this is dangerous, but I like doing it because I really want to know what your guys' problems are with data sets that you're running. And going from there. So hopefully you kind of see how these tools are useful for what you guys are doing. And if you have data sets that you think can be helped by these tools, please let me know. Again, I'm very happy to run data sets to show you what our new software algorithms can do for your problems. So again, if you do have a system with patterns saved, feel free to give us there. Okay, so questions, guys? I do have a question about this here, just kind of saying, hey, what are some of the differences here between the marble and the dolomite? Again, when you're dealing with indexing on something like this with a calcite dolomite, you can see the intensity changes are some of the bigger things, and the intensity changes here because you have this magnesium substitution for calcium. So again, the intensity changes are really what makes something like these bands change in their intensity. So again, higher Z, more backscatter essentially. So again, like over here on the dolomite, where we have this rotation, again, it's like, what am I seeing in these different spots going from there? And another just kind of a question about this map here is again, this is this here is a full area map. So this was done in a relatively large area. Again, this is basically a full geological thin section. And again, we can see here that we were able to find and get these really small details with that step size. So again, one of the advantages of doing large area mapping is I can do a very fine step size and then change my field of view and keep doing that over and over and over again. I forget exactly how many fields this was. I think it's like somewhere around 50 or so, and go from there. I just saw a question, then I closed it. I think I saw another question. Okay. Give me a second here. The box is a little bit small. Okay, so here's the questions. I've got two questions here, so I don't see the name on it. But this is how the full patterns obtained. Are they measured from standards? No. So for EBSD, let me make sure I just understand your question. Okay. So I assuming here you're talking about the master patterns. No, the master patterns are fully dynamically simulated. And what we mean by that is it's basically run through a Monte Carlo simulation of what's happening in the sample. So Kikuchi diffraction is kind of like a scattering event happening inside your sample. I kind of tell people it's three-dimensional Plinko. So again, this is probably a little bit more US-centric kind of explanation here, but your atomic positions in your lattice planes, you throw your electrons in there and they bounce around, and you can model basically how they come out. And in the end, you get these lines of deficit or lines of excess that basically show up on the phosphor screen and saying, hey, I'm having more electrons here or I'm less electrons here. In the end, we get to Kikuchi patterns. Well, we can model that. So we model our beam, we model our geometry, all that kind of stuff. And when you do that, you get those beautiful master patterns that I showed you. So these master patterns here, oops, let me go ahead, go back to these master patterns. These are fully modeled information here. Now, again, I think this is one of the things you actually start to see, but this is probably a little bit deeper than this talk is meant for. But there are actually some differences here between the dynamical simulation that we're seeing from kind of day-to-day work. So hopefully that kind of information here will kind of help us tweak these models a little bit more for more real-world solutions. But that's the nice thing about the experimental patterns is to get around this. So again, those master patterns are that. So again, these patterns over here on the left-hand side are collected from the EBSD camera itself. And there's a second part of your question up here. How's the experimental pattern matched to the full pattern? Yeah, that right there is it's basically it's an FFT using what's called a spherical harmonic approach. This is where I get a little bit hand wavy. I'm sorry for the clicking back and through this real quick, but it's the best way for me to do this. Sorry. There. So this is what's called spherical harmonics. It's basically a sampling method of using this, but again, in the end, it is using an FFT approach. But it has to be tweaked because of the way that again how we're doing this, because this right here, this master pattern is kind of like a spherical projection of the entirety of the diffraction sphere. That said, with our the way we sample it, we basically have to again kind of transform what we're doing on this. So again, we're doing a couple different things to it to figure out where we're getting to match A to B, so to speak, and then we're running it through the FFT things. And again, it's much more efficient calculation and faster. Again, this is where this gets to, again, the edges of my knowledge here. Again, if there's, it's hard to be an expert in everything, and this is where my knowledge starts to break down here, is this mathematical kind of approaches here. And this is, if you're interested, again, Will will talk to you about this for hours if you want to. But yeah, this is the paper here. It kind of talks a little bit more in details about how they do that. We should have a copy of that paper if you really wanted it. Okay, any other questions? Let me go back up here again. Sorry, I'm suffering from big monitor syndrome, where you have a big giant monitor, which means you have tiny little question box up in the top right corner. Cool. Any other questions, guys? If not, we're looking like we're going to wrap up. And again, if not, most of you guys have my email. And going from there, just making sure my moderator. Do you see any other questions, or are we good? Nope. Looks like a new question just came in. Ooh, good questions. Nice. Okay, so this is another question here. Okay, yeah, if there aren't more questions, Jonathan, I'm having trouble seeing them in this box. Let me see if I can open up this box differently. Yeah, so if you could paste the questions in the other chat, I'd appreciate it, Jonathan. So some question says, when choosing the NPAR solution, NL-PAR versus NPAR 1 through 9, third sample pattern, if correct. Okay, so what's the differences between NPAR and NL-PAR? So NPAR basically, again, so this is what we call a kernel approach. So NPAR is looking at just my nearest neighbors. So I have my pattern in the middle, I have the 6 nearest around that. So as you change what's called NL-PAR, or we call it nonlinear pattern averaging and reindexing, what you're doing is you're changing that kernel size. This is where I'm gonna get myself in trouble here because I can never remember the exact math. So the first one is, so the first kernel is 6, of course. And the next one I think is 11. And then, oh boy, I'm way off here. But as you increase that kernel size, you're basically increasing how many patterns you're using. Now, when we're doing this NPAR, there's a couple things we have to watch out for. Of course, main thing is am I still basically the same stuff? So there is a kind of a check there, basically saying, hey, is there enough correlation here that I should be using this pattern? So there's always kind of this yes or no kind of thing of like, should I include this pattern when I'm actually averaging all these patterns together? Now, the other thing is there is a weighted approach there. So if you look when you're doing an NL-PAR, there's this little weighting factor. It's basically how fast I decay it. So the patterns that are further away are weighted less than the patterns near me. So the amount, your question here is how many, what's the best one I should do? I can't answer that question. It's going to depend on your sampling density. So the more dense you're kind of sampling your sample, you may have higher quality patterns closer, so you might just be able to do like a kernel of 2 or 3. But maybe again, if you have like very larger grains that are very sparse sampling, you might want to do it over a large area. I don't think I've ever done an NL-PAR over about 3 or 4 myself, but that's kind of what I would usually do. And then, okay. Yeah, that question about the sampling of the brachiopod. This is a sample my colleague ran. I believe that data set was done by a broadbeam ion polisher, but do not hold me to that. A relatively small area, you can do something like that for geological materials. We're usually going to be a little bit trickier. Sample prep for almost all these is going to be done down to submicron levels. So we usually do, for most things geological, you kind of start with that probe quality polish. And for geological stuff, we usually would do what's called a vibratory polish with chloride silica after that. The issue with geological materials is again, the multi-phase nature of it makes it tricky to know how long I should be doing things for, and kind of go from there. Now, I'm always pretty straightforward with my mistakes. When you're doing this work here, you want to make sure that you do every step consistently and high quality. And when you're doing petrographic thin sections, you're doing it for light. So you're basically, this kind of goes back to this kind of the deeper question here of when you're dealing with geological sample prep, is again, most of the time we're doing our work, we're thinking about light prep. Not always, but we're doing light prep. So when you're doing that, again, you can kind of be a little bit lenient. that the word I'm looking for, on those kind of those bigger step sizes of polishing materials. But geological samples, again, when you're polishing is basically damaging your sample, right? You're scratching it over and over again, so that when your scratches are done, they're basically not visible to you using the wavelength of light that you're looking at here. Well, light is one thing, electrons is a different wavelength. So again, we want to make sure that the level that we're looking at is of higher quality. And there's also the depth of deformation when you're polishing something. So again, we're prepping geological EBSD samples. We want to make sure we're getting all those steps relatively well defined and consistent to get rid of those deformation layers as we go. But yeah, but getting back to your actual question, again, I think that brachiopod sample, I believe it was polished by a broad beam. And if I don't think Renee is here, but Matt, if you know as well, let me know. But I personally don't know any more information on there. Cool. With that, I don't see any more questions, and we're just right about here on time. Again, if you do have questions, again, feel free to reach out to us, and I will be happy to answer them. Again, I really hope you guys kind of see these tools here that we have and how they can help your work. Again, I think we can start to be able to ask questions on the geological side that previously we just kind of ignored because they were a little bit, the learning curve to do it maybe was there or was too tough, or again, the software wasn't really there to answer those questions. And now, we bent that learning curve. We have the tools available to start doing these harder geological questions. So please reach out. Let me know if you guys have data sets and all those kind of things, and go from there. But if not, I think we're done, guys. Again, thank you for your time. Very much appreciate you guys listening to me kind of talk to myself here for an hour, but really good questions. And again, thanks, guys.